This is the Neuronaut NX-1, a high-performance FPV flying wing shaped by artificial intelligence and built with only one goal: maximum aerodynamic efficiency. A few weeks ago, I posted a video about the design, build and maiden flight, link in the top right if you haven't seen it already, and I called it insanely efficient. And then the comments came in, asking for proof. Okay, fair enough, you wanted numbers. So here they are. In this video I'll compare the NX-1 with a well-known reference, the Zohd Dart 250G. We'll analyze both designs with the state-of-the-art tools, extract the key aerodynamic metrics, and bring in flight test data to back up the calculations. Call it, if you want, an efficiency reality check, a data-driven dogfight with the Dart 250G. To reverse engineer the famous Dart 250G, we'll use a process called photogrammetry. In simple terms, we take a bunch of overlapping photos from all around the wing. The software finds the same small features across shots and triangulates their position in 3D. This will give us a measurable digital model. This process is important because before we compare anything, we need real geometry so the numbers aren't guesswork. In my case, I took about 300 photos, the maximum the software allows, and that gave us a detailed point cloud of the model and its surroundings. With that, the software lets you convert the point cloud directly into a mesh, crop to the area you care about, and export the geometry as an STL. I then imported the wing into my CAD software and rebuilt the model using the 3D scan as the reference. This wasn't an easy process, and it involved a lot of hands-on measurements on the actual model. As you can see, the 3D scan is far from perfect, so I relied on the good old ruler and calipers to nail the key dimensions. But all in all, I believe the final CAD model is a faithful representation of the real thing. Having a CAD model of the Dart is essential. It turns a foam wing into numbers and fits our CFD tools for an apples-to-apples comparison. Okay, so now that we've got both wings in the digital world, let's line them up and see what the shapes are telling us. At first glance, they look about the same size, but let's dig into the parameters that drive their aerodynamic behavior. Regarding length and wingspan, they are similar in overall size, with the Dart just slightly smaller. Reference wing area is the same for both designs, at 8 square decimeters, so that gives the NX-1 a slightly higher aspect ratio. The drag coefficient has two main contributions, a parasitic drag plus an induced drag or drag due to lift. It's this second term where aspect ratio really matters. For the same amount of generated lift, increasing aspect ratio puts a bigger number in the denominator, so induced drag drops fast. That denominator also includes E, the Oswald efficiency factor. This is basically an indicator about how close the lift distribution is to the ideal elliptical one. E depends on planform twist, taper, sweep, washout, tip devices. The theoretical best is equal to 1, but real wings like ours typically sit around 0.7 to 0.9. Now we get to quarter core sweep, where they really diverge. The NX-1 has a positive 27 degrees of aft sweep, while the Dart shows negative 12 degrees. Aft sweep generally helps overall stability in flying wings, while forward sweep pulls lift inward and can help delay tip stall, two completely different design choices. They also differ significantly in tip twist or washout, with the NX-1 having more than twice the Darts. In theory, bigger washout lowers the tip's angle of attack, delaying tip stall, keeping elevons effective, and preserving roll control near stall. Elevon area is the percentage of the wing that will move to generate pitch and roll. The NX-1 uses 20%, while the Dart's only 8%, giving the NX-1 in theory more authority and requiring smaller deflections. The trade-off here are higher servo loads, but in cruise, with smaller trim deflections, they should actually reduce drag with respect to the Dart. Finally, we have a few global metrics such as the wetted area ratio, which is the total surface the air wraps on divided by the reference wing area, so lower means less skin friction drag for the same size. Next, overall weight, and more importantly, wing loading, which for fairness will fly both at about 3.5 kg per square meter. Okay, so now that we have compared the plan for an overall metrics, let's take a look at one of the most important design choices in any wing, the airfoil. As an aerodynamicist myself, I spend a lot of time tuning this. I could actually do a whole dedicated video on the design process. For the NX-1, I'm using a highly modified MH64. It's aimed at low Reynolds number, trims easily with a touch of up elevation thanks to its reflex, and targets high lift to drag ratio with a smooth, gentle stall. On the Dart, the airfoil is trickier to pin down since we didn't design it, so I uploaded a picture to ChatGPT and asked him to help me narrow the candidates using airfoil databases. After a few rounds, PW51 kept coming up as the best match. It is actually a great reflexed airfoil that prioritizes a broad, forgiving envelope and solid pitch stability. Great for handling, even if it trades a bit of peak efficiency. Now that we've inspected and analyzed both wings' geometry, it is time to pull out the real aero numbers, and today the go-to state-of-the-art way to get them is CFD. You can think about CFD, or computational fluid dynamics, as a virtual wind tunnel, a computer-based simulation technique used to analyze and predict the behavior of fluid flows by solving the Navier-Stokes equation numerically. These partial differential equations are derived from applying Newton's second law of motion to a fluid element, but believe me, they are exceptionally complicated due to nonlinearity, high dimensionality, coupling between equations, and especially turbulence, an extremely complex and chaotic regime. Predicting turbulence directly from Navier-Stokes is actually an unsolved challenge, and for a 3D problem, it is still unknown whether a smooth global solution always exists. So in practice, scientists and engineers often rely on numerical approximations instead of exact solutions. In our case, we first need to create a discretization or mesh of the region where the fluid flows occurs. We do this by creating a small, discrete cells or elements. Once the mesh is ready, we solve the governing equations numerically. For those asking, I normally use OpenFOAM for all my personal projects. There are many CFD packages out there, but this one is free, open source, and highly customizable. So meet the cluster. This is my big PC doing big boy math, this laptop that thinks is a workstation, and my wife's PC. Carefully borrowed under a signed peace treaty. Nope! Anyway, apologies to the power bill and big thanks to my wife for the borrowed compute time. I've now got a ton of CFD data for both designs, so let's dive into the aerodynamic results. In this animation, you are seeing the pressure coefficient distribution, CP, over our flying wing at cruise condition. This parameter measures how much the local pressure differs from the free stream pressure, scaled by the flight dynamic pressure. In plain terms, it is a speed-independent map of suction and push over our aircraft. Qualitatively, blue negative CP means low pressure or suction, while red positive CP means high pressure. So let's compare the two wings and see what the pressure maps tell us. At the aft end, the Dart shows a low pressure pocket that tends to pull the airplane rearward. You can also see it when we plot an isosurface of total pressure loss. It highlights the zones that contribute most to drag. Notice the concentrated patches around the aft fuselage and the junctions. Because this area is smaller on the NX-1, the resulting base drag is significantly lower. Under the fuselage, there is a broad blue region, low pressure, caused by the belly accelerating the flow. Ideally, you want higher pressure below and suction above, so the net force is upward, so this underbelly suction works against you. Up front at the nose, you see a large red patch of high pressure. This area is larger on the Dart, indicating a slightly higher parasitic drag. Finally, let's take a look at the most important area, the wings. The NX-1 shows a smoother, more uniform suction over the center body and mid-span, with lighter tips due to the washout. The Dart has a stronger inboard suction, but it is broken up at the fuselage, wing mounts, and vertical fin, so you get some discontinuities and pressure spikes here and there, not ideal for efficiency. Taking a look at the tip streamlines, you can clearly see the dart rolling up a strong tip vortex. The NX-1 higher aspect ratio, greater washout, and tip relief loading shed a weaker vortex, wasting less energy in the wake and, in theory, translating to lower induced drag. Visuals are great, and from what we have seen so far, the NX-1 should have better aerodynamic efficiency, but let's put the numbers on it and get the final verdict. And for that, we first need to explain how aerodynamic efficiency is really calculated. Our plane in a moving airstream feels two main aerodynamic forces: lift, perpendicular to the incoming flow, and drag, parallel to the flow, which opposes motion and slows the aircraft down. The incoming airstream speed is usually denoted as u infinity, and the angle between the wind chord line and that flow is known as alpha, or angle of attack. We can now define two key aerodynamic coefficients, such as the lift and drag coefficients. They are just the net forces scaled by the dynamic pressure and the referenced wind area. So the natural question now is, how do these coefficients change with angle of attack? Focusing first on the lift coefficient, as angle of attack increases, lift rises linearly over a useful range. However, beyond a critical angle, the stall, the boundary layer is no longer attached, the adverse pressure gradient grows and the flow separates on the upper wing surface. Both the maximum lift coefficient and the angle at which a stall occurs are key metrics for an aircraft. They set how slow you can fly before stall and how forgiving the wing feels as you approach that point. Drag behaves differently. As alpha increases, CD rises roughly quadratically because induced drag scales with the square of lift. Near stall, flow separation grows and the curve kinks sharply upward. Now we've got the two main ingredients to calculate the aerodynamic efficiency, which is the ratio between lift and drag. As angle of attack increases, efficiency rises from low values, reaches a peak, and then drops again as separation grows and drag climbs. That peak is the sweet spot, and it is where we normally want to fly during cruise to minimize energy consumption. So what do all the CFD simulations say when we put both wings head to head? If we take a look to the lift coefficient, in the linear range both curves are very close, but the NX-1 carries a touch more of CL at a given alpha. Near the limit, they both share the same maximum lift coefficient, but the dart peaks a little later, so the stall behavior should be more forgiving. You may have noticed that a CL max of 0.7 is quite low compared to conventional wings. The main reasons are the extremely low Reynolds number at which these wings are flying, plus the low aspect ratio which flattens the lift curve and caps significantly the maximum lift. Regarding drag, the NX-1 CD0 is actually about 20% lower, with the polar sitting below at the whole alpha range. Alright, time for reveal, the moment that no one has been waiting for. Which wing is actually more efficient? At cruise, the Dart sits near 6.9, while the NX-1 reaches a peak of 8.7. That's about 27% more efficiency. That's a huge increment if you ask me. Just to put it into perspective, from the 737NG to the 737 MAX, it is reported that all the aero modifications added up about 1 to 2% efficiency improvement, and they put a ton of effort to get there. So when we talk about a 27% jump, that's huge. Honestly, there is a massive amount of data I didn't even touch on here. If you're interested, I'll be happy to dive into those in future videos. For now, just keep in mind this cool looking plot, which serves as an overall flight comparison between both designs. And don't get me wrong, the Dart 250 is a magnificent wing. It's actually the one I use for my everyday flights. In future videos, I'll flight test both designs and compare them in the real world. I'm already logging data with the invaluable help of these two little assistants. If you want to support the channel, there is a Patreon link in the description where you can access all the scripts and data generated for this video. And if you want to download the NX-1 and build it yourself, you are in luck, there is a 15% discount the next 10 days. Thanks for joining me on this journey, and don't forget, stay curious, stay creative, and keep building the future. See you in the next one.